A shadow wider than our solar system hangs in the void. This is the mark of the universe's largest black holes, and they are so much more than cosmic monsters. They are the invisible architects, the silent engines that build and destroy galaxies. We are about to explore 25 mind-bending facts about these gravitational titans. You will understand how they warp reality itself, from their explosive births to their quiet fate billions of years from now. How did they grow so impossibly large so quickly? What happens when two of these giants finally collide? The answers redefine our place in the cosmos. What does it feel like to stand at the edge of a reality where the rules of physics break down? But before we get to the staggering numbers, we need to define what largest truly means out here. In the cosmos, size is not about physical width in the way you might think. A black hole's defining feature, its point of no return, is called the event horizon. Think of it not as a solid surface, but as an invisible spherical boundary. Once anything, even light, crosses that line, it can never come back. The size of a black hole, then, is really about two things: its sheer mass and the corresponding size of that event horizon. Now, black holes come in different weight classes. Stellar mass black holes are the remnants of exploded giant stars, and they can be a few times to maybe a few dozen times the mass of our Sun. Then there's a mysterious middle category, the intermediate mass black holes, which are elusive and thought to be the missing link. But the true titans, the ones that dominate this list, are the supermassive black holes. These are the gravitational anchors found at the very heart of nearly every large galaxy, including our own Milky Way. Their scale is almost incomprehensible. We are talking about monsters with masses millions, even billions of times greater than our Sun. For this journey, when we say largest, we are setting our sights on these supermassive giants. Their event horizons are so vast you could fit our entire solar system inside them with room to spare. This is the scale that warps galaxies and bends the fabric of the universe itself. At the very top of this gravitational mountain sits a champion. Meet TON 618, an ultramassive black hole so colossal it redefines the upper limits of what we thought was possible. Its statistics are almost impossible to internalize. TON 618 carries a mass of approximately 66 billion times that of our Sun. To put that into a human scale, if our Sun were a single grain of sand, TON 618 would be a mound of sand the size of a mountain. Its event horizon, that point of no return, is not just large, it is monstrously vast. The diameter of this invisible sphere is estimated to be over 1,300 times the distance from the Sun to Pluto. You could fit our entire solar system, every planet, every comet, every bit of the Kuiper belt, inside its shadow with room to spare. We found this behemoth not by seeing the black hole itself, but by witnessing the cosmic fireworks it creates. TON 618 is the engine of a hyper-luminous quasar, an object so bright it outshines the galaxy that hosts it. Billions of light years away, this quasar is a blazing beacon from the early universe. Its staggering light comes from the superheated material screaming into the abyss. As gas and dust spiral down at nearly the speed of light, they form a whirling, frenzied structure called an accretion disk. Friction within this disk heats the material to millions of degrees, causing it to glow with an intensity that can be seen across the cosmos. It is this brilliant, violent glow that allowed astronomers to pinpoint TON 618's location and calculate its impossible weight. This is not a quiet giant. It is a roaring furnace, a cosmic lighthouse whose beam has been traveling for over 10 billion years to reach our telescopes. Yet even a king can be challenged for its throne. In the distant Phoenix cluster, a galaxy cluster over 5.7 billion light-years away, lies a contender named Phoenix A. Some recent observations and calculations suggest this supermassive black hole might not just rival TON 618, it could potentially dethrone it. Estimates for its mass are staggering, ranging up to 100 billion times the mass of our Sun. If confirmed, that would make Phoenix the single most massive black hole humanity has ever identified. But why is there such a debate, such a wide range in the numbers? The challenge lies in the immense distance and the indirect ways we have to weigh these monsters. We cannot put them on a scale. Instead, astronomers measure the speed of stars whirling around the black hole's core, or study the motion of superheated gas in its accretion disk. For an object as far away as Phoenix A, nestled in the heart of a fantastically bright cluster, these signals are incredibly difficult to isolate and interpret with perfect precision. Different methods can yield different results, leaving room for scientific discussion. This uncertainty is not a flaw in our science, it is the frontier of discovery itself. What is not debated is the sheer cosmic power Phoenix A wields. The entire Phoenix cluster is a cauldron of extreme energy, and the black hole is its furnace. Vast amounts of intergalactic gas are being pulled toward the galaxy's center, feeding the beast and creating outbursts of energy so powerful they sculpt the landscape of the cluster itself. These outbursts heat the thin gas that floats between the galaxies to millions of degrees, preventing it from ever cooling down and collapsing to form new stars. Think of it as a cosmic thermostat set permanently to off for star formation. Phoenix A is not just a passive giant, it is an active tyrant, governing the fate of thousands of galaxies around it by controlling the very material from which future stars would be born. Its influence stretches across millions of light years, a silent decree written in superheated plasma. While these distant titans blaze with the fury of quasars, our own galactic home harbors a supermassive black hole of a very different temperament. At the heart of the Milky Way, a mere 27,000 light-years from Earth, sits Sagittarius A star. With a mass of around 4.1 million suns, it is a modest giant compared to the billion solar mass monsters we have just discussed. You could fit its event horizon inside the orbit of Mercury, yet its proximity makes it the most important black hole we will ever study, our very own laboratory for understanding these cosmic engines. For decades, astronomers could only infer its presence by watching the bizarre dance of stars around an invisible point of gravity. Then, in 2022, the Event Horizon Telescope collaboration did the impossible. They unveiled the first direct image of Sagittarius A star's shadow, a blurry but breathtaking ring of light encircling the dark heart of our galaxy. This was not a photograph in the traditional sense. It was a monumental feat of global coordination, using a virtual telescope the size of Earth itself to piece together the faint radio whispers coming from that immense gravity well. Sagittarius A star is remarkably quiet, a sleeping giant compared to the voracious quasars powering distant galaxies. It is not actively consuming large amounts of material, which is why our galactic center is not a blinding beacon. This quiet state, however, allows us to see the space around it with incredible clarity. That is where the true magic happens. Stars like one called S2 whip around this invisible point at speeds exceeding 15 million miles per hour at their closest approach. That is about 3% of the speed of light. Watching S2's elongated orbit over more than 27 years provided one of the most precise tests of Einstein's theory of general relativity ever conducted. As the star swings perilously close to the black hole, its light stretches to longer, redder wavelengths in a process called gravitational redshift, exactly as Einstein predicted. The star's path itself rotates over time, tracing a rosette pattern instead of a simple ellipse, another triumph for relativity. Our home black hole, for all its modest size, has become the ultimate proving ground for the laws of physics at their most extreme. It is a gentle giant that whispers the secrets of the universe if you know how to listen. The quiet dance of stars around Sagittarius A star reveals a profound truth. We can never see a black hole directly, but we can see its absolute command over everything nearby. So how do you weigh an invisible object trillions of miles away? Astronomers have become cosmic detectives, using the clues left in the light of captive stars and superheated gas. The most direct method relies on a principle as old as astronomy itself, Kepler's laws of planetary motion. Just as the speed of Earth's orbit tells us the mass of the Sun, the frantic speed of a star whipping around the galactic center tells us the mass of the gravity source holding it captive. By meticulously tracking a star's orbit over years or even decades, measuring its velocity and the size of its elliptical path, scientists can perform a simple but powerful calculation. The result is the mass of the invisible anchor at the orbit's focus. The faster the star moves and the closer it gets, the more massive the central black hole must be. This is how we pin down the 4.1 million solar mass weight of our own galactic center. But what about black holes in distant galaxies where individual stars are too faint to see? For those, astronomers look at the collective motion of entire clouds of gas or clusters of stars swirling in the galactic core. By analyzing the broad smear of their light, a signature of their incredible speeds, they can still deduce the gravitational pull of the monster within. For the most active feeding black holes, another ingenious method comes into play. Quasars blaze with light from their accretion disks, and within that brilliant glow are specific, telltale emission lines from elements like hydrogen. The searing heat and violent motion within the disk broadens these spectral lines into fat, fuzzy smears. The width of that smear is a direct measure of the gas's speed, which in turn reveals the mass of the black hole driving the entire chaotic engine. In some rare and valuable cases, nature provides an even more precise cosmic ruler. In a few galaxies, dense clouds of water vapor swirl near the central black hole. These clouds act as natural megamasers, amplifying microwave radiation like a cosmic laser. Because we can pinpoint their position and motion with exquisite accuracy, these megamasers allow for perhaps the most precise black hole mass measurements ever made, all by tracing the orbit of a cloud of water vapor billions of light years away. Each method is a testament to human ingenuity, a way of listening to the universe's subtle whispers to comprehend the silent giants that shape it. That point of no return is a border written into the fabric of the universe itself. The event horizon is not a solid surface you could crash into like the rocky crust of a planet. It is something far stranger, a one-way membrane in the geometry of space-time. Picture standing above a mighty waterfall, watching the river flow smoothly toward the precipice. As you approach the edge, the current becomes faster and faster, pulling everything toward the inevitable drop. The event horizon is that exact edge, but for reality. It is the line where the warping of space-time, caused by the black hole's immense mass, becomes so severe that every possible path forward, for anything with mass or even massless light, curves inexorably inward. There is no force in the universe that can propel something outward once it has crossed. To cross the horizon is to have the entire future cone of your existence, every path you could possibly take, point directly toward the central singularity. It is not that the black hole sucks things in like a cosmic vacuum cleaner. Instead, space itself is falling inward at the speed of light at that boundary, and you are simply riding the current. The size of this invisible boundary, known scientifically as the Schwarzschild radius, is determined by one thing alone: the black hole's mass. The relationship is beautifully simple. Double the mass and you double the radius of the event horizon. This linear scaling is why the largest supermassive black holes have shadows of such incomprehensible size. A black hole with a mass of 1 billion suns has an event horizon with a radius of about 3 billion kilometers. That is a sphere so vast it could comfortably contain the orbits of every planet out to Neptune with room to spare. For the true titans like TON 618, this boundary stretches farther than the entire reach of our solar system, a silent, dark sphere where the universe's rules of escape are permanently rewritten. This surprising gentleness reveals a cosmic irony about supermassive black holes. Their danger is not about their gravity reaching out to snatch you from across the galaxy. In fact, the gravitational pull from a distant supermassive black hole is no stronger than the pull from a star of the same mass. Its threat is intensely local, concentrated right at its event horizon. And here is the twist: because of their colossal size, crossing that horizon could be a surprisingly smooth experience. The terrifying process called spaghettification, where the difference in gravity between your head and feet stretches you into a noodle of atoms, would not happen at the boundary of a giant like TON 618. Its gravity is spread over such a vast area that the tidal forces, the stretching pull, are incredibly weak at the event horizon itself. You could drift across that ultimate point of no return without even a noticeable jolt. The real stretching and tearing would occur much deeper inside, closer to the mysterious singularity at its core. Now compare that to a stellar mass black hole, the corpse of a single star. Approaching its tiny, fierce event horizon is a violent death sentence. The tidal forces are so concentrated and severe that they would rip you apart long before you ever reach the point of no return. So the largest black holes in the universe are, in a bizarre way, the most physically gentle to fall into. But do not mistake gentleness for safety. The true lethal reach of an active supermassive black hole comes not from its gravity but from its fury. A feeding quasar blasts out unimaginable amounts of radiation across the entire electromagnetic spectrum, from searing X-rays to powerful gamma rays. This energy can sterilize entire galaxies, boiling away atmospheres and scouring planetary surfaces clean from distances of tens of thousands of light years. It is not the invisible grip of gravity you need to fear from these giants, but their blinding, cancerous light. That radiation is the real signature of their power, a beacon of creation and destruction that shapes cosmic evolution on the grandest scales. Their gentle crossing hides an even deeper cosmic puzzle. If falling into a giant black hole is a smooth ride, how did these giants themselves form in the first place? The origin of supermassive black holes is one of the most profound mysteries in modern astrophysics. We have found quasars powered by black holes billions of times the Sun's mass, shining from when the universe was less than 1 billion years old. That is an astonishingly short time on the cosmic clock. It leaves scientists with a pressing question: how did they grow so impossibly large so fast? Our standard model for black hole formation starts with the death of a massive star, creating a stellar mass seed of maybe 10 to 100 solar masses. But for that seed to grow into a billion solar mass monster within a few 100 million years, it would have to eat at a ferocious, nearly impossible rate, pushing against fundamental limits set by the radiation its own feeding would produce. This timeline is so tight it has forced astronomers to consider wilder, more dramatic birth scenarios for these cosmic titans. One leading theory skips the star entirely. In the dense, pristine soup of the early universe, before the first stars flickered on, enormous clouds of pure hydrogen and helium could have collapsed directly under their own immense weight. Without heavy elements to help them cool and fragment into stars, these primordial clouds could have crumpled into a single, monstrous object, a direct collapse black hole seed with a starting weight of tens of thousands, maybe even 100,000 suns. This gives the growing black hole a colossal head start, a seed already the size of a small galaxy's core, ready to feast on the surrounding gas. Another theory suggests that in the crowded, violent nurseries of the first galaxies, early stellar mass black holes could have merged together repeatedly and rapidly, snowballing in size through a frenzy of collisions. They could have also gorged on the dense, cold gas that filled those young galaxies, accreting material at breakneck speeds in an era when the rules of physics allowed for a more chaotic and rapid feast. Yet the discovery of quasars like J0313, a beacon from when the universe was only 670 million years old and powered by a black hole already over 1.6 billion solar masses, continues to strain even these exotic theories. It is a cosmic detective story where the evidence, written in ancient light, challenges our very understanding of how structure emerges in the infant universe. Each of these theories paints a picture of a more extreme, more dynamic cosmic dawn than we once imagined. That ancient light from the dawn of time carries a specific, brilliant signature. It is the mark of a quasar, the single most powerful and persistent source of energy in the known universe. At its heart lies not a new kind of object, but a familiar one in its most extreme state. A quasar is simply the active, blazing core of a distant galaxy, an active galactic nucleus where a supermassive black hole is engaged in a feast of cosmic proportions. When these titans pull in vast amounts of gas, dust, and even entire stars, that material does not fall straight in. Instead, it forms a whirling, flattened disk of superheated plasma, spiraling around the black hole at nearly the speed of light. This structure is the accretion disk, and it is the engine of the quasar's unbelievable power. As particles in the disk rub violently against each other under the immense gravitational strain, friction heats them to temperatures of millions of degrees. This process alone creates a ferocious glow, but the true brilliance comes from the black hole's incredible efficiency. As matter in the inner disk is compressed and heated beyond imagination, a significant portion of its mass is converted directly into pure energy following Einstein's famous equation. This energy erupts as light across the entire electromagnetic spectrum, from radio waves up to deadly gamma rays. The result is a beacon that can outshine the combined light of every single star in its host galaxy by a factor of 1,000 or more. For a time, the central black hole becomes the brightest thing for billions of light years in every direction, a lighthouse whose beam cuts across the cosmos. This is why quasars are our primary tool for finding the most distant and massive black holes. In the vast, dark sea of the early universe, we cannot see the faint, sprawling arms of their host galaxies. But we can easily spot the dazzling, pinpoint brilliance of their cores, the quasars, signaling the presence of a gravitational giant gorging itself at the dawn of creation. The blinding light of a quasar is only half the story of a black hole's fury. Some of these active giants perform an even more spectacular feat, launching twin beams of matter and energy from their poles at speeds so close to light it defies belief. These are relativistic jets, and they are the universe's most powerful particle accelerators. Not every feeding black hole produces them, but when they do, the effect is monumental. The engine for this cosmic cannon lies in the chaos of the accretion disk. As superheated plasma swirls inward, powerful magnetic fields become twisted and coiled by the black hole's own rapid spin. This creates a natural funnel, a focused channel along the black hole's axis of rotation. Instead of falling into the abyss, some of the infalling material gets caught in these magnetic whirlwinds and is redirected, blasted outward in two opposing beams perpendicular to the disk. The process taps into the raw rotational energy of the black hole itself, launching charged particles to velocities exceeding 99% the speed of light. The result is a searing beam that can stretch for hundreds of thousands, even millions of light years into the intergalactic void, but the journey does not end there. When these ultra-fast jets finally plow into the thin gas that floats between galaxies, they slam into a wall. The collision is violent and spectacular. The jet material spreads out, forming gigantic, balloon-like structures known as radio lobes. These lobes, often glowing brightly in radio waves, can be larger than the galaxy that spawned them, visible across cosmic distances as a testament to an ancient eruption. The energy deposited by these jets is not just for show. It acts as a cosmic feedback mechanism, pumping heat and turbulence into the galaxy's reservoir of star-forming gas. This can effectively shut down star formation by preventing the gas from cooling and collapsing into new stars. In this way, the supermassive black hole, through its incredible jets, can dictate the life cycle of its entire host galaxy, transitioning it from a vibrant, star-making factory into a quiet, aging elliptical galaxy. From a single point of infinite darkness, a force emerges that sculpts the fate of hundreds of billions of stars. This galactic thermostat has a formal name in astrophysics, active galactic nucleus feedback, and it is one of the most important discoveries in understanding how our universe evolved. The process is a breathtaking example of cosmic balance. A supermassive black hole feasts on surrounding gas, but that very feast powers jets and winds that blast energy back out into the galaxy. This energy heats the vast reservoirs of cold gas, the raw material for new stars, making it too hot and turbulent to collapse under its own gravity. Imagine trying to build a delicate snowflake in the middle of a roaring bonfire. That is what active galactic nucleus feedback does to star formation. It puts the brakes on. This explains a long-standing mystery about the giant elliptical galaxies we see in the nearby universe. These massive, smooth, football-shaped collections of stars are famously red and dead, filled with ancient, aging stars and showing almost no signs of new stellar birth. For decades, astronomers wondered why. The answer lies in their supermassive black holes. In the past, these black holes were likely incredibly active, their furious jets and radiation effectively sterilizing their own galaxies by shutting down the star-making factories. The black hole, in a sense, regulated its own food supply and the future of its home. Without this feedback, theoretical models suggest that galaxies would consume their gas too quickly, forming stars in a brief, brilliant burst before sputtering out. They would also grow far more massive than the galaxies we actually observe. Active galactic nucleus feedback provides the necessary pressure, a cosmic form of tough love that prevents runaway growth and creates the diverse population of galaxies we see today. The largest black holes are not passive tenants at the center of cities of stars. They are the master urban planners, using their fearsome energy output to zone entire galaxies, deciding where and when new construction can occur, and ultimately determining a galaxy's destiny across billions of years. This cosmic symbiosis between a black hole and its galaxy is not random luck. It is a fundamental rule written into the architecture of the universe itself, a discovery so profound it reshaped our entire view of cosmic evolution. Astronomers call it the M-sigma relation. In simple terms, it reveals a remarkably tight correlation between the mass of a galaxy's central bulge, the dense, spherical swarm of older stars at its core, and the mass of the supermassive black hole that lives there. The larger the stellar bulge, the more massive its central black hole tends to be. This relationship holds true across an astonishing range of galaxies, from small spirals to giant ellipticals. It is as if, for billions of years, the black hole and its host galaxy have been growing in lockstep, like two children holding hands as they mature. This cannot be a coincidence. It is direct evidence that the black hole and the galaxy are not separate entities. They are a single, interconnected system, evolving together through a complex cosmic dance. The black hole is not just a passenger in the galactic core. It is an integral part of the galaxy's very identity, its mass mysteriously tuned to the mass of the stars swirling around it. This discovery pointed toward a deep, underlying physics that forces the two to communicate, to influence each other's growth across the eons. It is the ultimate signature of the feedback process we just explored, but written in the final, settled structure of mature galaxies. The M-sigma relation is the fossil record of that epic conversation. The M-sigma relation connects giants to their galactic homes, but a crucial piece of the puzzle has been frustratingly absent. Between the stellar mass remnants of dead stars and the supermassive giants in galactic cores, there should exist a middle class, the intermediate mass black holes. These are the missing links, with masses ranging from about 100 to 100,000 times our Sun. They are the predicted stepping stones, the seeds from which the supermassive titans could have grown through countless mergers over cosmic time. Yet finding them has proven extraordinarily difficult. They occupy an awkward cosmic niche, too large to form from a single collapsing star under normal circumstances, but too small to power the brilliant, unmistakable beacons of quasars. An intermediate mass black hole feeding on a trickle of gas would glow with a faint, diffuse light, easily lost in the glare of its host star cluster or small galaxy. So astronomers have turned detective, searching for them in the most likely hiding places. Dense globular clusters, ancient spherical swarms of hundreds of thousands of stars are prime candidates. In these crowded stellar cities, gravitational interactions could have forced smaller black holes to merge over eons, building up an intermediate mass anchor at the cluster's heart. Some dwarf galaxies, the small, faint building blocks of larger galaxies like our own, may also harbor these middleweight black holes, a relic from their ancient past. The hunt has yielded tantalizing clues, like unexplained motions of stars at the core of a few globular clusters, or ultra-luminous X-ray sources in nearby galaxies that flicker in ways a stellar mass black hole cannot explain. But definitive proof, a clear measurement of an intermediate mass black hole's gravitational grip, remains elusive. Finding them is not just about completing a cosmic census. It is about testing the very story of how the universe's largest structures came to be. Did supermassive black holes indeed grow from these smaller seeds, feasting and merging their way to dominance? Or did they spring into existence already colossal from the direct collapse of primordial gas? Each candidate intermediate mass black hole is a potential answer, a silent witness to the ancient growth spurts of the cosmos's most powerful engines. The hunt for those missing links points toward an even more spectacular cosmic event. When galaxies themselves collide, their central black holes are destined for a dance of ultimate consequence. Galaxy mergers are common in our dynamic universe, and as two vast star systems slowly coalesce over billions of years, their supermassive black holes are drawn toward the new combined center of gravity. At first, they orbit each other at a vast distance, separated by thousands of light years. But as they swing through the dense stellar core of the merged galaxy, they begin to lose energy, slowly spiraling inward over an almost incomprehensible timescale. This is the in-spiral, a gravitational waltz that can last for eons. For most of this dance, the black holes are too far apart to feel each other's direct pull strongly. They nudge nearby stars, flinging them away through complex gravitational interactions, and this loss of orbital energy causes the black holes to gradually creep closer. The final stages, however, require a different mechanism. When they get within about 1 light year of each other, they have exhausted the supply of stars to scatter. Their progression toward merger seems like it might stall, a problem astronomers call the final parsec problem. The likely solution is that vast amounts of gas funneled into the core by the galactic collision provides the final break. As the black holes plow through this dense medium, dynamical friction slows them just enough to bring them within the range where they can finally begin to scream their presence to the universe through gravitational waves. These are not the same ripples detected by observatories like LIGO. When stellar mass black holes merge, they create high-frequency chirps lasting a fraction of a second. The merger of supermassive black holes is a deeper, slower, and infinitely more powerful event. Imagine the deepest note from the largest possible cello, stretched across years or even decades. These mergers produce gravitational waves at much lower frequencies, far below what any ground-based detector can hear, as the Earth's own background noise would drown them out. To listen for these cosmic monsters, we must go to space. The Future Laser Interferometer Space Antenna, or LISA, is designed for exactly this purpose. It will consist of 3 spacecraft flying in a vast triangular formation, millions of kilometers apart, using lasers to measure minute distortions in spacetime itself. When a pair of supermassive black holes in a distant galaxy finally complete their billion-year in-spiral and coalesce, the resulting shockwave in spacetime will sweep through the LISA constellation. The signal will be a slow, building siren song, growing in amplitude and frequency as the black holes get closer and faster, culminating in a final, universe-shaking crash. The energy released in that single moment will briefly outshine the combined light of every star in the observable universe. It will be the most powerful event since the Big Bang, not in light but in the pure distortion of the fabric of reality. Detecting these waves will do more than confirm a theory. It will open a new window onto the hidden population of binary supermassive black holes, letting us witness the final act of galactic evolution and hear the echoes of ancient collisions that built the galaxies we see today. That final, universe-shaking crash would release energy in a form more fundamental than light. But even the mightiest black holes are not eternal. They face a slow, cold fate predicted by one of the greatest scientific minds of our time. Stephen Hawking made a startling theoretical leap, applying the strange rules of quantum mechanics to the immense gravity of a black hole. His conclusion was revolutionary. Black holes are not perfectly black. They should emit a faint, ghostly glow of particles, now known as Hawking radiation. The mechanism hinges on a bizarre quantum quirk. Empty space, according to quantum theory, is not truly empty. It is a seething sea of virtual particles, pairs of particles and antiparticles that constantly wink into and out of existence, borrowing energy from the vacuum before annihilating each other and paying it back. This happens everywhere all the time, but at the very edge of an event horizon, something extraordinary can occur. One of these virtual particles might appear just outside the horizon, while its partner appears just inside. The particle outside can escape, stealing a tiny amount of the black hole's energy to become real. Its trapped partner with negative energy falls inward. From the perspective of a distant observer, the black hole has just emitted a particle. To pay for that particle's existence, the black hole loses a minuscule amount of mass. This is Hawking radiation, a quantum whisper from the abyss. For a stellar mass black hole, this glow is unimaginably faint, far colder than the cosmic microwave background. But over staggering eons, this slow leak of mass means black holes can, in theory, evaporate. This leads to one of the deepest puzzles in all of physics, the black hole information paradox. In quantum mechanics, information about a system, the specific details of every particle that went into it, is never truly lost. It can be scrambled, but it must be preserved in principle. Yet if a black hole evaporates entirely through Hawking radiation, which is purely thermal and contains no information about what fell in, then all the detailed data about every star, planet, or atom it ever consumed would be permanently erased from the universe. This violates a core tenet of quantum theory. Physicists have been wrestling with this paradox for decades. Some suggest the information is encoded on the event horizon itself, a holographic imprint slowly released in the radiation. Others propose it escapes into a baby universe or is preserved in a final remnant. The debate continues, a fundamental clash between gravity and quantum mechanics. For the supermassive black holes we have been discussing, this entire process is almost irrelevant on any human timescale. Their Hawking radiation is so incredibly weak, their temperature so close to absolute zero, that they would take many orders of magnitude longer than the current age of the universe to evaporate even a fraction of their mass. We are talking about timescales of 10 to the 100th power years, numbers so vast they have no meaning in our reality. Their fate is not evaporation, but a cold, dark dominance that will last until the cosmos itself grows old and dim. That slow evaporation is a whisper against the cosmic thunder of their creation. Where do we find these ultimate giants? Look toward the universe's grandest metropolises. The largest black holes of all do not reside in beautiful spiral galaxies like our Milky Way with its delicate, star-studded arms. They make their home in the colossal, amorphous blobs known as giant elliptical galaxies. These are the universe's ancient, retired cities, often sitting like monarchs at the very heart of massive galaxy clusters, the largest gravitationally bound structures in existence. Think of a spiral galaxy as a vibrant, bustling port city, still building new docks and ships. A giant elliptical is more like a vast, sprawling capital, its frenetic construction long finished, now defined by immense scale and quiet, enduring power. This is no coincidence. The correlation is a direct result of a violent past. Giant elliptical galaxies are almost exclusively the products of catastrophic mergers, the head-on collisions and subsequent cannibalism of multiple large galaxies over billions of years. Each merger is a cosmic disaster that funnels a tsunami of gas directly toward the newly combined galactic core. This provides a feast of almost unimaginable proportions for the central black hole, allowing it to gorge and grow to ultramassive sizes. Simultaneously, the chaotic gravitational forces of the merger tear apart the elegant spiral structures, scattering stars into a vast, diffuse, and spherical halo. The result is a smooth, featureless giant, a galaxy shaped like a three-dimensional football, containing trillions of ancient stars but very little of the cold gas needed to make new ones. The supermassive black hole at its center, now grown to titanic proportions, becomes the permanent gravitational anchor for this entire stellar empire. It is the silent, dark engine at the heart of the universe's largest cities, its mass a direct record of the colossal feasts provided by the galactic collisions that built its home. The furious blaze of a quasar is not a permanent state but a brilliant, fleeting chapter. These cosmic engines have a life cycle, and like any fire, they can only burn as long as there is fuel to feed them. When the vast rivers of gas and dust flowing into the galactic center are finally exhausted, or when powerful jets blow away the remaining fuel, the feast comes to an end. The brilliant accretion disk, that whirling maelstrom of superheated plasma, begins to thin and fade. Without fresh material to heat through friction and violent compression, its blinding light dims. The quasar shuts off. What remains is a dormant supermassive black hole, a quiet giant resting at the heart of its galaxy. This is precisely the state of our own Sagittarius A star. It is not dead, it is simply sleeping, its immense gravity still holding court over the surrounding stars, but no longer producing the spectacular fireworks of its youth. This dormancy is actually the norm in our present-day universe. Most large galaxies around us now host quiescent central black holes. The era of ubiquitous, blazing quasars peaked about 10 billion years ago, when the universe was richer in cold, dense gas and galactic collisions were more frequent. Today, that frenetic period of construction and feasting is largely over. The transition from a brilliant quasar to a silent titan marks a galaxy's entry into a calm, stable middle age. The central black hole, having grown to a size that reflects its galactic home, now rests, its job of regulating star formation largely complete. It becomes a dark monument to the galaxy's violent past, a sleeping sovereign whose reign is felt through gravity alone, waiting for the distant possibility of a new infusion of gas to stir it from its slumber. The quiet slumber of most black holes makes their direct observation a monumental challenge. But in April 2019, humanity's collective ingenuity tore aside the veil. The Event Horizon Telescope collaboration unveiled the first ever direct image of a black hole's shadow, a landmark achievement that felt like science fiction made real. The target was not our own quiet Sagittarius A star, but the far more massive and active black hole at the heart of the giant elliptical galaxy Messier 87, known as M87 star. This titan, weighing in at 6.5 billion solar masses, offered a larger, clearer target against the sky. Capturing its shadow required a telescope the size of our planet. The EHT is not a single instrument, but a global network of 8 radio observatories spanning from the mountains of Hawaii and Arizona to the high deserts of Chile, the frozen landscape of the South Pole, and across Europe. By synchronizing these telescopes with atomic clocks and pointing them all at M87 star for several nights, scientists effectively created a single Earth-sized virtual dish. This technique, called very long baseline interferometry, provided the angular resolution needed to see something as seemingly small as a donut on the surface of the Moon. The data collected was so vast it could not be sent over the internet. It had to be physically shipped on hard drives to central processing centers. The resulting image, a blurry but unmistakable orange ring of fire surrounding a dark central void, instantly became an icon. That bright ring is not the event horizon itself. It is the photon ring, the signature of superheated gas in the accretion disk whirling at near light speed. The black hole's immense gravity bends the light from both the front and the back of this disk, wrapping it around the abyss to create that brilliant, complete circle. The dark central shadow is the true revelation. It is about 2.5 times larger than the actual event horizon. This enlargement is the direct work of extreme gravitational lensing, a prediction of Einstein's general relativity. The black hole's gravity is so powerful it captures any light ray that passes too close, creating this shadow of absence that is, paradoxically, larger than the point of no return. We were not seeing the black hole, we were seeing its overwhelming grip on the very fabric of space and light. That shadow captured in the M87 image is the ultimate example of a black hole's power over light. This phenomenon has a name, gravitational lensing, and it is one of the most elegant confirmations of Einstein's vision. The largest black holes and the immense galaxies that host them do not just absorb light. They bend it. According to general relativity, mass warps the very fabric of spacetime. Think of placing a heavy bowling ball on a stretched rubber sheet. The sheet curves. Now roll a marble across that curved surface. Its path will bend around the depression. Light travels along the contours of spacetime, so when it passes near a massive object like a galaxy cluster with a central supermassive black hole, its path is curved. The black hole and its galaxy become a natural cosmic magnifying glass, a gravitational lens. The effects can be breathtakingly beautiful and scientifically priceless. When a distant galaxy is perfectly aligned behind such a massive foreground object, the light from that background galaxy gets bent around all sides of the lens. Instead of a single, distorted smear, the light can reassemble into a complete circle of fire, an Einstein ring. It is a perfect halo of warped reality, a signature written in starlight that a colossal mass sits between us and the source. More often, the alignment is slightly off, creating multiple mirrored images of the same distant galaxy, arrayed around the lens like cosmic jewels. For astronomers, this is not just a pretty picture, it is a fundamental tool. The lens magnifies the light of objects that would otherwise be far too faint and distant to see, acting as nature's own free telescope. By studying these distorted, magnified images of galaxies from the very early universe, we can peer further back in time than any human-built observatory could manage alone. But the lens also reveals secrets about the lens itself. By measuring how severely the light is bent, scientists can map the distribution of mass in the foreground galaxy cluster, including the vast halos of invisible dark matter that hold these structures together. The silent, dark gravity of the supermassive black hole at the cluster's heart plays a crucial role in this cosmic distortion. Every stretched arc and duplicated image is a direct message, a testament to how these titans mold the geometry of the cosmos and, in doing so, grant us a clearer view into the deepest reaches of space and time. This cosmic lens bends reality, but the object at its heart defies it with an almost shocking simplicity. The universe's largest black holes, for all their terrifying power and complex influence, are among the simplest objects in existence according to a profound idea called the no-hair theorem. It is a whimsical name for a deeply serious concept, suggesting that a black hole has no distinguishing features, no frizz or flare, no individual personality. In the harsh language of physics, it states that a black hole in perfect isolation can be completely described by just three numbers: its mass, its electric charge, and its spin, or angular momentum. Everything else, every single detail about the material that collapsed to form it or that later fell in, is permanently erased. The intricate history of a billion suns, the chemical composition of swallowed planets, the very atoms of any astronaut unfortunate enough to cross the horizon, all of it is reduced to three simple values. The black hole does not remember. It becomes a perfect, featureless pit in space-time. For the supermassive black holes we find in nature, this simplification goes even further. Astrophysical black holes are not expected to carry any significant net electric charge, as any excess would quickly attract opposite charges and neutralize itself. So in practice, these titans are defined by just two properties: how much they weigh and how fast they are spinning. Think of the difference between describing a living, breathing human being with a lifetime of memories, experiences, and scars, and describing a bowling ball. You could describe the bowling ball with its weight and whether it is spinning as it rolls down the lane. That is essentially the level of detail the no-hair theorem allows for a black hole. The most complex, destructive objects in the cosmos are, from the outside, the simplest to describe. All the rich, messy information about what went into them is locked away behind the event horizon, lost to the external universe. This is both a beautiful simplification and the root of that profound information paradox, a reminder that in the face of such immense gravity, the universe seems to prioritize elegant geometry over historical record. Mass and spin define the universe's simplest objects, but that spin hides a ferocious power. While a black hole's mass determines the size of its event horizon, its rotation warps spacetime in a far more active way. A spinning black hole, described by what physicists call a Kerr solution, does not just sit in space. It actively drags the fabric of spacetime around with it, like a colossal spoon stirring a vat of thick honey. This phenomenon is known as frame dragging. Near the event horizon, space itself is pulled into a whirling motion, forcing any nearby object or even light to move in the direction of the spin. It is a tangible testament to Einstein's vision, where mass and energy do not just bend space, they can twist it. This rotational energy is not locked away forever. In a theoretical process that sounds like pure science fiction, energy can be stolen from a spinning black hole. The mechanism relies on those intense magnetic fields we discussed earlier, fields anchored in the black hole's own accretion disk. As the black hole's spinning spacetime twists these magnetic field lines, it can launch jets of plasma with breathtaking efficiency. This is the Blandford-Zenagic process, and it is thought to be the primary engine behind the most powerful relativistic jets we observe. In this scenario, the black hole's spin acts like a gigantic battery, its rotational energy converted directly into the raw power that lights up radio lobes millions of light-years across. The implications are staggering. A spinning black hole can theoretically provide even more energy than the superheated material in its accretion disk alone. It taps into a fundamental reservoir of power written into the very rotation of spacetime. This spin is also a hidden history book. The direction and speed of a supermassive black hole's spin tell a story of its past. Did it grow steadily by feasting on gas swirling in from a consistent direction, like a steady wind spinning a turbine that would have spun it up to incredible speeds? Or was its growth chaotic, dominated by mergers with other black holes coming from random angles? Those violent collisions can sometimes slow a black hole down or even flip its axis entirely. By measuring spin, astronomers can look back at the diet and the dramatic events that shaped these titans over billions of years. The silent, dark vortex at a galaxy's center is not just a weight. It is a dynamo, a cosmic flywheel storing the kinetic memory of everything that ever fell into it. A black hole's power is not about pulling you in from across the galaxy. This is perhaps the most persistent myth about these cosmic giants, the idea of the black hole as an all-consuming cosmic vacuum cleaner, actively sucking everything into its maw. That image is dramatic, but it is fundamentally wrong. Black holes do not suck. They are not cosmic predators hunting for prey. They are simply objects of immense mass, and they obey the same law of gravity as the sun, Earth, or an apple falling from a tree. Their gravity is extraordinarily strong only because it is concentrated in such a small, unfathomably dense point. But the nature of that gravitational pull is no different in kind from any other object. It is an attractive force that depends on mass and distance. If you magically replaced our sun with a black hole of exactly the same mass, the gravitational anchor for our solar system would remain unchanged. The Earth and every other planet would continue orbiting that point of darkness in exactly the same path it does today. The catastrophic change would not be our orbit but our source of light and heat. We would be plunged into permanent, frozen night, but our celestial dance would go on uninterrupted. So why does matter ever fall into a black hole at all? The answer lies in a concept called angular momentum. In the vast emptiness of space, almost nothing falls straight down. Gas, dust, and even stars are almost always moving sideways relative to the black hole, carrying too much rotational energy to simply drop in. Think of trying to drop a marble directly into a small drain at the center of a large, flat sink. If you just set the marble down near the edge, it will not move. If you give it a push, it will most likely whirl around the sink, orbiting the drain rather than falling straight in. To get the marble to spiral inward, you need a way to slow its sideways motion, to rob it of that orbital energy. In space, that slowing force is often friction. As material is drawn toward a black hole, it collides with other material, creating a swirling, chaotic traffic jam. This is the accretion disk. The violent collisions within this disk generate immense heat and light, but they also act as a brake, gradually stripping away angular momentum and allowing the gas to spiral slowly inward. The phenomenal energy of a quasar or the fury of a jet does not come from some supernatural sucking force. It comes from the conversion of gravitational potential energy into radiation and motion as matter finally loses that long orbital battle and plummets toward the event horizon. The black hole is not an active hunter. It is a patient, inevitable endpoint, a dark pit at the bottom of a cosmic hill where everything that loses its footing eventually rolls. Their patient gravity will one day face a universe with nothing left to give. The ultimate destiny of the largest black holes is written in the slow, cold fade of all things, a chapter in the story of the heat death of the universe. Picture our cosmos tens of billions of years from now. The accelerating expansion of space has pulled galaxies so far apart that the night sky in any surviving star system goes utterly black. All stars have long since burned out, from the brilliant blue giants to the last faint red dwarfs. The interstellar gas, the raw material for new suns and planets, has been entirely consumed, locked away in stellar remnants, or flung into the endless void between galactic superclusters. In this era of cosmic decay, the supermassive black holes at the hearts of those now dark galaxies face a profound change. With no gas left to accrete, no stars left to tidally disrupt, their brilliant accretion disks vanish forever. The quasars and jets, the great beacons of the universe's youth, are silent. The giants become completely dormant, resting in perfect darkness as their immense gravity continues to bind the ghostly halos of dead stars and cold planets. They become the final, dark monuments of their former empires. Yet even in this state of perfect isolation, a faint quantum whisper persists. Hawking radiation, that trickle of particles born from the vacuum at the event horizon, continues its unimaginably slow work. For a stellar mass black hole, this evaporation might take a mere 10 to the 67th years. But for a supermassive black hole with billions of solar masses, the timescale stretches into the realm of pure abstraction. We are talking about 10 to the 100th years, a number so vast it has no analog in human experience. It is a 1 followed by 100 zeros. To call it a number of years is almost misleading, as it dwarfs every other timescale in cosmology. In this distant, dark era, the largest black holes will be the last major structures to fade from the cosmos. They will outlive every star, every planet, every brown dwarf, and even every stellar remnant like white dwarfs and neutron stars, which will themselves have decayed through processes like proton decay over much shorter spans. The universe will be an increasingly dilute sea of subatomic particles and photons, growing colder and colder, and at its center, for eons upon eons, will be these dark, shrinking titans. Their final evaporation, when it comes for the very last one, will be a silent, unobserved event, a flash of particles so feeble it would be lost in the vast, empty cold. It marks the point when the universe achieves its maximum state of entropy, a uniform, lifeless equilibrium where nothing ever happens again. The story that began with a fiery, dense singularity ends in a strange symmetry with the quiet disappearance of the last one. Their final, silent evaporation leaves a profound question about their beginning. What if these giants were not merely born into a structured cosmos, but were the very architects that built it? This leads us to a staggering possibility that supermassive black holes in their blazing youth helped sculpt the universe itself. After the Big Bang, the cosmos was a hot, opaque plasma. As it expanded and cooled, protons and electrons combined to form neutral hydrogen, and the universe plunged into its so-called dark ages. For hundreds of millions of years, no stars or galaxies shone. The first luminous objects to pierce this pervasive gloom were not just stars, but the brilliant quasars powered by the earliest supermassive black holes. Their emergence was a cosmic revolution. The intense ultraviolet radiation from these first quasars began to blast apart the neutral hydrogen atoms, reionizing the universe and making the intergalactic medium transparent once more, ending the Dark Ages. This was a fundamental phase change for the entire cosmos, and the black holes were the primary engines driving it. Their light did not just illuminate the darkness, it fundamentally altered the state of matter across billions of light years, clearing the fog and setting the stage for future galaxies to be seen. But their influence may have run even deeper into the very skeleton of reality. The universe today is not a random scattering of galaxies. It is a vast cosmic web, an intricate tapestry of dense filaments and immense empty voids. How did this structure form? The leading theory points to tiny quantum fluctuations in the primordial universe, stretched by inflation, which provided the seeds for gravity to build upon. Yet the incredible power of early quasars might have acted as a cosmic feedback mechanism on a universal scale. Their ferocious jets and radiation could have pumped enormous energy into the surrounding gas, heating it, stirring it, and preventing it from collapsing into galaxies in some regions, while perhaps triggering collapse in others. Think of a pot of boiling water. The heat from the bottom creates rising columns and swirling currents, organizing the chaos. In a similar way, the concentrated energy from these early black holes could have helped sculpt the distribution of matter, amplifying certain patterns in the infant cosmos. They may have helped carve out the great voids and define the dense filaments where galaxies would later line up like pearls on a string. In this view, the supermassive black holes were not passive residents that formed after the cosmic web was built. They were active participants, their explosive output helping to chisel the large-scale structure we inherit today. They were not just inhabitants of the cosmic landscape, they were its master sculptors, using light and fury to shape the universe in its infancy. Sculpting the cosmos is one thing, but explaining its darkest heart is another. The universe's largest black holes are not just objects of immense power, they are also profound puzzles, cosmic question marks that push our current laws of physics to their absolute breaking point. For all we have learned, their deepest secrets remain locked away behind the event horizon, in a realm where Einstein's elegant equations of general relativity collide with the bizarre, probabilistic rules of quantum mechanics. This collision creates a frontier of mystery, a space where science must admit its limits and where speculation, guided by mathematics, takes flight. Could these titans be more than just endpoints? In some highly speculative theories, the extreme warping of spacetime at the core of a black hole might not culminate in a point of infinite density. Instead, it could theoretically open a bridge, a wormhole, connecting two distant points in our own universe, or even serving as a gateway to an entirely separate cosmos. The mathematics allows for such structures, known as Einstein-Rosen bridges, but the reality is far more daunting. Any naturally occurring wormhole linked to a black hole would be catastrophically unstable, collapsing in an instant under its own gravitational weight. To hold it open would require a form of exotic matter with negative energy density, something we have never observed. So while the idea fuels science fiction and stretches our imagination, it remains a fascinating mathematical possibility rather than an observed phenomenon. The true mystery lies deeper at the very center. General relativity predicts that all the matter crushed within a black hole converges on a singularity, a point of zero volume and infinite density. Here, the very concepts of space and time as we know them cease to have meaning. Our physics simply shatters. This is not a failure of science, but a signpost. It tells us we are missing a crucial piece of the puzzle, a theory of quantum gravity that can marry the vast scale of general relativity with the tiny realm of quantum physics. What truly happens at the core? Does matter get crushed into entirely new forms, or does it pass into some other state of existence? Is the singularity a real physical object, or merely a sign that our equations are incomplete? We do not yet know. These unanswered questions are not a dead end. They are the very engine of discovery, reminding us that the largest black holes are not just features of our universe. They are invitations to rewrite our understanding of reality itself. The profound mysteries at a black hole's core are not just abstract puzzles. They are a direct challenge to our understanding of reality, and that is precisely why studying these titans matters so deeply. This is not a passive observation of distant monsters. It is an active, relentless probe into the most extreme environments the universe can produce. Every flicker of light from a quasar, every wobble in a star's orbit, every faint ripple in spacetime is a test. It is a test of Einstein's theory of general relativity under conditions of gravity so severe they cannot be replicated anywhere else in the cosmos. When we watch a star like S2 whip around our galactic center, its path tracing a rosette instead of a perfect ellipse, we are not just collecting data. We are witnessing a century-old prediction play out in real time, confirming that our mathematical description of gravity holds true even at the very edge of a 4 million solar mass abyss. The shadow cast by M87 star, perfectly matching the predicted size from relativity, is not just a pretty picture. It is a rigorous examination, and so far, Einstein's vision has passed every single test. But the quest is far from over. The next generation of observatories, like the space-based gravitational wave detector LISA, will listen for the collisions of supermassive black holes. Any deviation from the predicted signal, any whisper that does not fit the model, could be the clue that leads us to a deeper law of physics, a theory that finally unites gravity with the quantum world. In this pursuit, the largest black holes are our ultimate laboratory, a natural particle accelerator and gravity well of unmatched scale. They force our theories to prove themselves in the arena where they are most likely to break. Beyond testing fundamental physics, these giants tell the life story of the cosmos itself. They are the hidden engines of galactic evolution. By studying the correlation between a black hole's mass and its host galaxy, we unravel the intimate billion-year dance between a destroyer and its creation. We learn how a galaxy is born from chaos, how it is shaped and quieted by the very monster at its heart, and how it eventually enters a long, dark retirement. The feedback from these black holes explains why some galaxies are vibrant spirals and others are red and dead ellipticals. It is a narrative of construction and regulation written in gravitational waves and ancient light. To understand black holes is to read the biography of galaxies, including our own Milky Way. This quest also drives our technology to its limits and beyond. The Event Horizon Telescope did not exist until the ambition to see the unseeable forced us to invent it. The same global synchronization of radio telescopes, the same petabytes of data, the same algorithms to piece together a shadow, these were all born from a single, profound question. That technological push has ripple effects, advancing computing, data storage, and precision engineering in ways that eventually benefit other fields of science and society. But perhaps the most human reason to study these distant titans is to find our own context. In a universe that hosts shadows wider than solar systems and energies that outshine galaxies, our world seems impossibly small and fragile. Yet here we are on a pale blue dot, using the light gathered by mirrors and antennas to comprehend forces that dwarf our entire existence. This act of cosmic curiosity, of reaching out with mathematics and imagination to understand the most violent and powerful objects in creation, defines something essential about us. It reminds us that we are not just inhabitants of the universe, we are its conscious part, striving to map the darkness and listen to its silent, gravitational song. The story of the largest black holes is ultimately a story about our own relentless need to explore, to know our place in the vast, dynamic, and beautiful cosmos we call home. From the silent, dark hearts of galaxies to the brilliant beacons that ended the cosmic dark ages, these 25 facts have taken us on a journey across scales that defy comprehension. We have stood before shadows wider than solar systems, witnessed the gentle tyranny of a black hole that governs star formation across millions of light years, and grappled with singularities where our very laws of physics dissolve. This exploration reveals a profound truth. The universe's largest black holes are not mere cosmic accidents or destructive endpoints. They are fundamental architects. Their gravity builds the galactic cores they anchor. Their explosive energy sculpts the large-scale structure of the cosmos. Their quiet feedback determines whether a galaxy blazes with new stars or fades into a red and dead retirement. They are creators as much as destroyers, woven into the very fabric of cosmic evolution. For every question answered about their mass or their spin, a deeper mystery emerges from the event horizon, challenging us to look further. Our quest to understand them is a testament to human curiosity, a drive to map the darkness with mathematics and light, to listen for the echoes of ancient collisions in the ripples of space-time itself. It is a reminder that we are part of this grand, dynamic story, striving to comprehend the forces that shaped our galactic home. What do you find most astonishing about these cosmic titans? Share your thoughts and questions in the comments below. If this journey through the extremes of space captivated you, please like this video, subscribe for more explorations into the universe's deepest mysteries, and share it with someone who wonders about the darkness between